Okay, I'll go ahead and get us started with today's Spatial Analytics and Data Seminar Series. Thank you for joining us. Today, I'm very happy to welcome Dr. Clio Andris. Dr. Andris is Assistant Professor in City and Regional Planning and the School of Interactive Computing at Georgia Tech. Her work falls broadly into the areas of geographic information science and technology, with research on mathematical models of social networks, social flows, and interpersonal relationships in geographic space, applied to urban planning, visualization, transportation, and geography. She's published widely in computational and urban analytics journals, including Computers, Environment, and Urban Systems, +1, Environment and Planning B, and many others. Dr. Andris received her PhD from MIT in Urban Information Systems and has held postdocs at the Singapore MIT Alliance for Research and Technology at the Santa Fe Institute. Please join me in welcoming Dr. Andris to today's SAD 2020 seminar series. And as I mentioned a minute or two ago, if you could please drop your questions and comments into the Q&A functionality on your menu bar, that will allow us to have a nice conversation when Dr. Andris is done with her presentation. And so with that, I will stop sharing and allow you, Dr. Andris, to share your slides.
Okay, we'll get started here. Okay, thank you so much to Dr. Franklin and Dr. Wolf, to Rachel and Levi for having me. This has been such a great seminar series this semester. It has been very happy despite its acronym. So we very much appreciate it. So analyzing interpersonal ties and social networks in using GIS. And so this is a passion of mine that I'm really glad to talk with you about today. So the agenda today is to give an overview of interpersonal ties and social networks in geographic space. This is going to be a little bit of a long introduction because we are not really used to modeling personal ties in GIS. We haven't really learned about modeling social networks in GIS super well. Then I'll give an example of mentorships and how to analyze those with GIS, and an example of a Mafia network that has a social network component on it. I also had a descriptive example of college romantic relationships in geographic space, but it ended up being a little bit more qualitative than quantitative. So we'll save that for later if we have time. So let's talk a little bit about why interpersonal relationships are really important in geographic space. This on the left is an example of a map in the New York Times from Descartes Labs that gave the percentage of residents who are not in the local area in May due to COVID. And the narrative behind this was that the wealthy moved out. So they didn't want to stay there. They had homes, other places, et cetera, and they had the agency to leave. But when you look at the number of single family households, or number of households where people were actually living by themselves. So this here is the percentage of households that just have one person in them. So it's up to 99%, and there's an 100% over here. And then, so more than half of households, which in these red areas tend to be living alone, they tend to match up. And it shows that not only, while these people may also have had higher income, they may have been leaving too because they wanted to be with other people. So it changes the narrative a little bit. Let's talk a little bit about what a social network is. Some people, when they hear the term social network, might just think, oh, Facebook or LinkedIn, that's a social network. We view it more as a clinical system. So a system of nodes linked together by edges. This is one of the first, what we call a sociogram. So a social network laid out on paper from Joseph Moreno in 1934. And he was looking at the class structure of first graders. So we have boys and girls in these different shapes here and looking at who nominated who as friendships. And he saw that the girls tended to nominate more of the girls and the boys tended to nominate more of the boys. So it gives us an overarching understanding of what a social network sort of looks like. These have a lot of known properties like 6 degrees of separation. We know that from social networks. And then how popular is the most popular person? And there's a lot of mathematical models behind social networks. So I have this problem now that, hang on a second. Okay, I can't see what my titles look like, but that's okay. So we'll guess what the titles are. So what is an interpersonal relationship, or what is an interpersonal tie? So these are your friends, families, coworkers, romantic relationships, and relationships through organizations, let's say like Alcoholics Anonymous or like a religious association. So those are our relationships. We have a lot of relationships in census data that we sometimes use and we sometimes don't. These are grandparents as primary caretakers. So the percentage of grandparents as primary caretakers in the US. And areas that are darker here show the higher percentage where the grandparents take care of the children. And so this shows where the grandparent-child relationships can be very strong and different than when the parent is a primary caretaker. We see in Indigenous communities, this is a very high rates. We see in the South, in a lot of African-American communities, this is in high rates. And then we've also seen growing rates in Appalachia, and we think that that might be due to the opioid epidemic. So you can also measure tie strength. So how, not just a tie, a link between two people, but how strong is that tie? In a social network of your phone calls or LinkedIn, for example, you may have equal tie strength with everybody across the network. But in reality, you're closer with some people than others. So we talk about the frequency, how often you contact them, how close you are, intimacy, whether it's a reciprocal relationship or one person always just calls the other person. We have also seen from online social media what tends to constitute a strong relationship or a weak relationship. So in one study, they ground truthed it with what people were doing online with their relationships with how strong the relationship actually was in real life. So they asked people, and they found out that having a lot of comments on posts and having a lot of messages between people tended to reveal a stronger relationship. So the goal here is we can add weights on relationships as well. So why situate a social network or a spatial or a social tie in geographic space? The goal is to discover how ties are influenced by geography. So we already know how human settlement is influenced by geography. We already know where agriculture occurs versus where the CBD is. We already know the roles of mountains and water and climate in helping us understand where human settlement occurs. But how does geography influence social ties? And also, this is a harder question, I believe, is how is geography influenced by ties? Like chain migration sets up an ethnic enclave. We don't know too much about that, but it's an interesting question. Another goal is to work towards a more canonical set of expectations and rules about the principles of relating over geographic space. So we already have principles of city scaling, for example. We have principles of road networks. We need better principles of how we relate over geographic space. So we have some basic hypotheses here. The first hypothesis is that ties are homophilous, meaning that social ties tend to occur between people that have similar socio-demographic or professional, etc., types of characteristics. So here's an example of a high school friendship network. And this has no spatial reference to it whatsoever. It's just spread out in terms of a force-directed network visualization. And the different colors here are race. So this is showing in this high school network that race is a big indicator of who has nominated who as their friend. And that is driving a lot of connections in the network. If we put it in geographic space, we could also show how segregation is at play, where family members exist between the people, and that's driving a lot of the connections. School bus routes, whether they went to elementary school with each other, those may also be factors that play into this. So it doesn't necessarily exist that they all just came together at the school and this is how it turned out. There's a lot of geographic factors at play here too. Ties also have propinquity. I hadn't heard of this term as a geographer or a GIS analyst until I started reading about social networks. Propinquity means that nearness creates more social ties, or that being close together means that you are more likely to connect. So let's take a look at propinquity in this example. So propinquity is not necessarily the same across geographic space. So this is a really cool example from Facebook networks from Mike Bailey et al. That was shown in the New York Times. So for every county in the US here, this is the share of friends who live within 50 miles, the share of Facebook friends who live within 50 miles. And when you see very white areas, it just means that the Facebook friends in that county have most of their Facebook friends up to 82, a little bit further than 82, 85, et cetera, friends, Facebook friends that also live within 50 miles. So this is a lot of locality. This is, I don't mean to pop this up as a cherry-picked example, but this is where Penn State is, right in the middle of central Pennsylvania. Wonderful place, highly recommended. But you can see that right around it, people have a lot of local ties. But in Center County, where Penn State is located, the large university, a lot of the Facebook friends are elsewhere. And you could see other counties like that popping up all over the US. And then in the western part of the US, we don't have that same type of nearness and propinquity. So tie presence also might decay with boundaries. We've seen that in a lot of our spatial interaction models, but we need to know it more for personal ties. So these could be infrastructural boundaries, administrative boundaries, physical and socioeconomic boundaries. The same kind of data here, the same kind of data did show us in this interactive graphic from the New York Times, showed us administrative boundaries as well. So this is showing that at the Pennsylvania border, there's much fewer ties. If you were to go over this, you would see that the mountains tend to mean that there are fewer ties, and you could see that social regions tend to mean that there are fewer ties as well. And then finally, ties follow a network. So that would be a basic hypothesis as well, is that if you were to sample some social ties out of a system, they may follow commuter networks. They may follow migration networks. They may follow some sort of economic networks, like a giant phone call network, for example, or a trade network. So those are our sort of hypotheses about how ties are spread out in geographic space. So now let's talk about how we're going to analyze them. Our technical objectives here are to embed the social network into GIS and the ties into GIS, do some common GIS functions like a spatial join between so that the ties can absorb the underlying features, and maybe compute cost distance between ties. When you see a lot of spatial social network examples, especially from the physics community or from the applied mathematics community, they're really interesting. They're really great mathematical things. They tend to use Euclidean distance a lot, and just upgrading to cost distance might be a little bit better. Let's take a look at one of my favorite examples here. This is we'll look at it in just a second there. Let's talk first about how to embed it in GIS. So decide what your nodes are going to be. Is it an activity space? Is it a real-time location? Is it someone's home address? Jittered, of course. Is it an administrative locale? Most of the things that I've seen tend to use the administrative locale, like which county are you in, which zip code are you in? Decide what your edges are going to be between the people. Is it evidence of a tie from self-report? Did they say they were friends with someone? Is it someone's emergency contacts? Is it something administrative from administrative records? Is it social media or telecommunications data that you have? How do you know that these people are connected, and to what extent? And then codify how your edges interact with geography. This is the part where the space really hits the rubber and the space really hit the road. Does the pedestrian path really matter between you? Are you going to fly to see each other? Or do we need to does it matter whether you're in driving distance or not? How is that line in GIS going to interact with the other features in the GIS? So here's an example of a tractor sharing network. This was done by a group of wonderful sociologists at UNC Chapel Hill. They had a long project over many years on the Nanrong district in Thailand. And they were looking at the different social networks in geographic space. And it's just really, this project is exemplary. So this example here shows a tractor sharing network. And it's directed, meaning that one person shared it with someone else, one person loaned it to someone else. And we know that because we can see the arrows here. Beneath it is land use. So they have an agricultural system where the red here is rice, the blue is water, and then the green is forest. And they showed how the people living in the forest and how this land use here tended to dictate a little bit of this tractor sharing network. And it showed that people didn't necessarily share a tractor with their nearest neighbor. They may have had to go farther to get a tractor loaned to them. And it showed how the land use helped this system play out. This project also looked at ties over water bodies like rivers, and then the importance of religious facilities in helping to create that social network. And they all use GIS for this, which is great. Visualization is also a really important part of this. This is an example of organized crime in geographic space, and this is a very popular paper. This paper examined gangs in Los Angeles, and what it did was it took the center of the gang's turf, so that is the nodes here, and what the lines between them are rivalries. So it showed the violence between the gangs and the rivalry that it had in the geographic space. So we can answer the question of, are nearby gangs more likely to be rivals than others? And what kinds of space might be unsafe if there are a lot of rival gangs there? This isn't a complete network, and there was no statistical analysis on it in this paper, but just visualizing it can help us get a better understanding of where the concentration of the rivalries are, where they're spread out, and whether they can tend to skip over space or not. So we also want to take a look at new metrics and retrofitted metrics for this. So I'll be presenting a couple today, like allometric distance, scan statistics, and the network flattening ratio. We'll also talk a little bit about new models to compare expectation from normal origin destination matrices and spatial social networks. One huge problem in this research is that we have so few actual spatial social networks with which to compare. So we don't have a great norm. And so we end up kind of doing a lot of simulation, saying if this was Poisson distributed, what would it look like? If this was normally distributed, what would it look like, et cetera. But this is a long year plan, many year plan that we have to look at together. So let's talk a little bit about a case study of dyads. So this was a question of how a mentorship program, Big Brothers, Big Sisters, which is a mentorship program that's been around for decades in the US, and it exists outside of the US. And what it does is that it'll pair a youth at risk with a member of the community, a volunteer member of the community, so that they can create a pair and have like a good relationship with them. The big, which is the volunteer in the community, takes the little, which is the child, out to do things on the weekends. They can help with their homework. They go to the zoo. They just have a good relationship. And it's a very popular program in the US. There's over 1 million matches at the moment in the US. So we wanted to see, does this organization make the city more cohesive? And our thinking behind that was that these relationships don't happen by happenstance. They weren't necessarily curated by someone in the social network, like, oh, this is a friend of a friend, or this is a friend of my aunt's or something. These were created inorganically by an organization. So we wanted to see if this type of organization, like another organization like Meals on Wheels, or again, Alcoholics Anonymous, something like that, is actually forging relationships within the city that wouldn't happen otherwise. So we had over 6,000 ties, so about 12,000 individuals over 7 cities, and we wanted to look at this analytically. And I'll just show you what these maps are, but I'll go over them a little bit more at the end. We have Kansas City here, and the black dots are where a big lives, and the red dots are where a little lives, and in the background are the 2017 ACS per capita income. And this is called Troost Avenue right here. And it is a big divider between socioeconomic, it's a big socioeconomic boundary between African Americans and white neighbors, and also, as you can see, income as well. So we'll see if they're stretching across that socioeconomic boundary. In Houston, we have the bigs living in the middle of the city, and then we have some of the littles on the periphery. And then here's an example in Tampa, we can see that the bigs are also living in certain areas of the city near the water, and then the littles aren't as well. And then these are just visualizations of the connections between them. All this research needs better visualization. It has a big haystack effect problem, and it could deal with more curvature and flow bundling, et cetera. So here are the tests that we did. We wanted to see if the pairs were farther away than a typical pair. We wanted to see if it took longer to get to them than a typical pair, if the travel distance and travel time was farther than we thought. And what do we mean by a typical pair? We worried about this quite a bit. What is a typical pair in the city? So one route we could have gone down on that route was to say, okay, we picked any two people in the city, or we picked any young person and any person over 18 in the city, and we did this simulation for them. We decided not to go that route. Instead, we permuted our own network so that bigs could be paired with bigs, littles could be paired with littles, and any big could be paired with any little. So neither is great. The problem with the entire population is that it doesn't necessarily represent the people who would have signed up for this program. The problem in that presented a problem because people in the suburbs, we thought these empty nesters were going to really dig in, and we didn't see that. I'll get to that in a second. The problem with just taking it from our own data is that our own data, we don't really know how it represents the greater population. And so it seemed a little cherry picked to do it that way as well, but that's how we did it. The allometric distance. So we calculated the allometric distance between every pair in our simulation and then every real pair that we had. Allometric distance is pretty fun. So what we did for allometric distance means that we calculated the number of people who live between the two, the big and the little, or the big and the big, the little, any pair. And so that's the kind of the intervening population. So they could be really far apart, but not have a lot of people between them, or they could be really close together and have a lot of people between them. So that was just a very simple GIS type of GIS operation where we picked up the census block population that the line was over. Now, if you're a GIS modeling geek, you can think of a bunch of ways to do that. So does the line go through the census block? Does it this and that? How are you prorating this? How are you doing asymmetric modeling, et cetera, et cetera? We did it very simply. So those are our distance metrics. Our hypothesis was that the actual pairs were going farther away, that they were really pulling from different parts of the city and just making this thing way more cohesive. Then we had administrative boundaries. Our hypothesis was that these pairs that were curated were more likely to cross administrative boundaries. And we wanted to do school districts for this, but unfortunately it was really hard to get that for all the cities, so we did counties. So to see if they crossed counties or not. Then we had a spatial interaction. We wanted again to have some sort of network that was showing telephone calls and social ties to see if these followed the traditional social networks. We couldn't get that either, so we used commuter flows. So are the ties, would they flow in the network here? And then finally, socioeconomic estimation. So are ties, do they tend to exist between places with similar socioeconomics, or do they tend to exist between places with different socioeconomics? And our variables were income, percent African-American, percent 25 and up with a bachelor's degree, and unemployment rate. These are our answers. This is a very big graph. I understand that. But this is how it worked out. So we mentioned that we had 7 cities. These are the cities here. The number of pairs that we have between them are at the top. And then what we did was we just multiplied this for every one person. We had 100 simulations go around. And so what we have the number of pairs that have a higher Euclidean distance than the simulated pairs, the pairs that have greater travel time, travel distance, et cetera, allometric distance. So let's just take a look at these 4 distance metrics. So we found a significant difference between our simulated pairs and our actual pairs. Our hypothesis was wrong. The actual pairs were way closer together than the simulated pairs. And we talked to Big Brothers, Big Sisters about this, and they said that they tend to want to match people who are close by each other, just so they can pick people, the bigs can pick up the littles a little easier. So our hypothesis was wrong there. And the Big Brothers, Big Sisters didn't necessarily know it was going to be wrong because they just have a tendency in these meetings, but it turned out to be that no, these pairs, the actual pairs, tend to be very, very close together. Did they cross administrative boundaries greater or less likely? We didn't find a whole lot of interesting evidence there. We had a likelihood that the actual pairs crossed the boundary and that the simulated pairs crossed the boundary. And there was nothing super impressive there, except for that the actual pairs were a lot less likely to cross county boundaries. The actual pairs were a lot less likely to cross county boundaries. Yes. Okay, spatial interaction with commuters. So this one turned out to be that they have completely different networks. So the interaction with the commuter network and our network, they didn't interact very well. We found that they were quite different. But the more interesting part here was the difference in median household income, bachelor's degree, percent unemployed, and percent African-American. We found that even though that they were very, very close by, our actual pairs were a lot more likely to have stark differences in socioeconomics. And this was just from the census data. So they lived in places with very different percent bachelor's degrees. They lived in places with very different median household incomes, differences in percentage employment, and mostly differences in percentage African-American. Los Angeles didn't show a change in there, but if we had included more of the Hispanic ethnicity, we may have been able to find a different result there. So the goal of this was to say, hey, are these pairs, are they making the city more cohesive? Are they going all across the city? Are they bringing together social networks and people that wouldn't know each other otherwise? And the answer is that in terms of distance, no, they're not doing anything interesting like, oh, that neighborhood's all the way over there. But in terms of socioeconomics, they are bridging people that have bridging neighborhoods, let's say, bridging neighborhoods that have different socioeconomic backgrounds. And just to dig in a little bit more, we already saw this one, these different pairs here. We found this radial effect in Houston. We found it across a couple of different cities, actually. It was actually very stark in Philadelphia too. This M here stands for mentor and the orange stands for protege. When you work with a very smart British scientist, he tends to give you big, nice words to use. So the orange here are the littles and the blue here are the bigs. And what we saw from this is that there was a little bit of a storytelling component in here that is that the younger generations, like the millennials in this data set, they moved downtown, they're kind of seen by some as gentrifiers, et cetera. They really stepped up and volunteered a lot in this network. And we saw that in some cases, more of the empty nesters and people in the suburbs were volunteering a little bit too, but not as much as we had originally hypothesized that women and men who had their kids go off to college and they lived alone now, or the elderly, weren't really engaging with this as much as the younger people who are living downtown. And we saw that play out in a couple of different cities. So a takeaway here is that when you have an administrative documents or evidence of ties in a social network, or just ties between two people, and you can geolocate them, you can use different tests to better understand what the dynamics of the relationships are vis-a-vis the city. Are they just random in there? Or are they connecting neighborhoods that wouldn't be connected otherwise, et cetera? And just one or two more notes about this is that all of these household locations are jittered a little bit, so the actual locations aren't being shown. Also, we don't, for this type of research, we don't release the year that the data was collected. So it could be any year in the past, we usually say any year in the past decade, so that we can add a little bit of an extra layer of privacy there. So we have that jittering, and we don't release when the data was collected. Okay, let's move on to a case study of a social network. And again, if we have time at the end, I'll be happy to show you our romantic relationships map too. So this particular case study is called "To Racketeer Among Friends, Spatial Features of Criminal Collaboration in the American Mafia." And this started out as a collaboration with sociologist Dan Della Posta at Penn State. And he casually mentioned to me that he was working on Mafia data. And I asked in the social network Mafia, and I mentioned, oh, do you have addresses for them? And he said, yes. And so I said, well, that's very exciting. We should work together. And it ended up being a really great collaboration. So what he did was he took dossiers of Mafia reports that were compiled in the 1960s, early 1960s, by the Federal Bureau of Narcotics. And they are the FBI now. And this was called La Cosa Nostra. We know them as the American Italian Mafia. So the network was created from lists of criminal associates. So this is an example of Big Frank over here. And it gives when he was born, some critical statistics here. It gives the residence, so the place that he lives. And so we were able to geolocate where they lived. It also showed some places where they frequent, for example, the Cuckoo Club, the Hula Hut, the Java Club in San Diego. We weren't able to geolocate these very well because they are not here anymore, but it would have given for a nice activity space. Then down here under criminal associates, he was able to create that network. So saying who has nominated who as a criminal associate. And so here we have the network. There's also been coded some other types of what their business was and who their kin is. So the addresses, we geolocated them using an API. We didn't think that the addresses changed a lot from the 1960s. Our network in this particular example has about 680 members. The original network had closer to 1,000, but there were some without addresses. There were some that were node isolates, so we cut those out. It's non-directional, meaning that there's no arrows between them. If somebody nominated someone, they're a pair. The ties aren't weighted, so there's no kind of, oh, they were very close associates and they were weak associates. The network includes one woman, the rest were men. The age ranged from about 18 to 80. About half were born in Italy, and most of them had fronts, like importing olive oil and cheese. Imports were a big deal. A couple ran ice cream parlors, a lot of restaurants, a lot of, the Java Club and the Hula Hut here. But this was a very violent group of people. So here's what the network looks like. This was done in GEFI. So it's 680. It includes 2699 edges. The average degree, so the average number of connections, is a little under 7. The highest connected person had 77. And the average path length, so number of hops to get from someone else, like that's your Kevin Bacon sort of number, is 3.88. New York's 5 families tended to comprise most of this network. So the big 5 families in New York, which I'll go over, tended to comprise most of it. The color here is showing the family that it belonged to, that each node belonged to. And then the size of the node is its degree, so the number of connections it has. And the way it's spread out is just, again, kind of a physicsy, force-directed sort of layout. Curvature doesn't mean anything here, but we can see that the family system, again, these nodes are colored by family, means that it's very highly dictates the network, what family you are in. And the families did tend to be in cities. All right. Typically, if somebody who was interested in mathematics and networks was going to analyze this network, this is what they would give us back, this edge distance distribution. They would say, oh, most of the people are very close. Here is the density. This is a PDF here, probability density function. This is on log scale down here. Oh, they're all very close. Congratulations. There's a couple of hops over here, and we're done with geography. That's it. But since we do GIS, we can go a step further. This shows the network in geographic space. And this was made in Kepler GL by Bei-Chen Tian. And it shows how this network is laid out. The blue are within family ties, and the red are between family ties. And this is where Joey Bonanno lived after he was exiled from the Bonanno family in New York City. He moved to Tucson alone. And then this is what the network looks like in New York. There is a lot going on in New York. All right, I've got about 5 minutes left, so I'll try to get through this pretty quick. So these are some of the bosses of the member families. So as I mentioned, there's 5 major New York families, and a lot of our analysis was relegated to New York because we didn't have to deal with that whole US scale issue. We could sort of just focus the scale where we had more of a consistent density. So the Bonannos, the Gambinos, the Genovese, Lucchese, and Profaci families. Those were the big 5 families. And so here we have the different members colored by what their family was. The Profaci family was mostly relegated to the southern part of Brooklyn. We can see the Genovese family all over the place, the Lucchese family all over the place, same with the Gambino and Bonanno families. We calculated the distance between the bosses, where the bosses lived or the highest degree members, and the median center of the family. And we found that they do tend to be close because they all live in New York, and this family was all over the place. But they don't tend to be right on top of the median center. And oftentimes the median center is not a great way to capture a point pattern. Sometimes it can be a terrible way to capture a point pattern, but it got us a little bit closer to using GIS to put some numbers onto this. We did see just visually, however, that some of the bosses tended to live near the water. And we were thinking that that may be due to imports and exports and closer access to the ports. We did also do an analysis on whether they lived in higher income neighborhoods or not, and they didn't. The higher degree individuals did not live in higher income neighborhoods, and they didn't tend to live in denser or non-denser neighborhoods than the rest of the people. The second thing we did here were new scan statistics, and this is something that I'm very excited about. So where are nearby criminal associates and where do dense cliques exist? So what we're doing here is we're using a focal window to find the number of edges in a radius and the network density within a radius. Now, like any good scan statistics and moving window analysis, you have to vary your neighborhood. You have to change the Euclidean distances, you have to change the network distances, you have to change the K nearest neighbors. And we did do that for sensitivity too. For example, here are some of the agents that are living in South Brooklyn over here called Diker Heights. And if you had Giuseppe Profaci here, you wanted to know the 2-kilometer neighbors, they might be in orange here. And if you had 1-kilometer neighbors, they might be here in blue. So you can see that changing that window size is going to change the neighbors you have. So we gave 2 newish statistics. Edge scan isn't super new, but the ND scan we think is pretty new. Normally, when you have a focal window, you would just count the number of dots in it and say, this is our density. Or you might do something more fancy and say, this is our kernel density. What we did was we counted the number of edges within the window to say, where are there many local connections? And then we also took the number of connections and then divided it by how many connections there could possibly be. And that's the network density. So since there's 5 edges here, the answer to this would be 5. The network density here would be 0.178. I'll go through this real quick here. So given 2 examples, one is Manhattan distance up here, one is K nearest neighbors of 10. These are results from edge scan. So this shows the parts of the network where there are a lot of edges. And we can see some concentrated places where there are a lot of edges. When you don't have to search for your 10 nearest neighbors, you get a lot more concentrated answers. When you do have to go out and search for your 10 nearest neighbors, the answers are more distributed. These are some photos. This is also from the ND scan, the network density scan. So this is saying, given how many potential edges we have, how many actual edges we have. And so we're able to find connected communities by doing this. This is a little bit of the sensitivity analysis here. And then this is sort of the variance that we have. And this sensitivity analysis just shows the edge scan for different window radii, K nearest neighbors, et cetera, to see how sensitive it is. But this is one of the last slides I'll show. And this says, why is this exciting? It's not done yet. We need more. But the red dots here are showing where our node scan and edge scan type of answers were statistically significant. And then the squares underneath here are showing where they would find statistically significant dot density. So statistically significant points. And we find that the answers are different. So the areas where there are red over here, and then there's a little bit of a kind of orangey square down there, they were hotspots in terms of this network, but they weren't connected hotspots. So the connected hotspots are these red type of things here. So this needs more work. It needs a little bit better statistics, but it's on its way. All right. So what I'm going to do now is just finish up. I wanted to let people know that we're putting all this into an R tutorial. If you're a Python person, yeah. So it's in an R tutorial, and we presented this a couple of weeks ago. It's not finished yet, but we presented it at a visualization conference, IEEE Viz, and it's not completely ready yet, but if you search for IEEE MoViz, you'll be able to see it. And we are just going to conclude. GIS lets us tell a better story. It helps us measure how ties follow spatial features. Some ties may follow typical rules, others may not follow these rules. And then why not? Why aren't they following the rules? Social networks have complex rules, and we want to show how they form differently due to geographic features. I think that the same social network or the same group of people may form a different social network given if they were in a different place. And that's something I really want to investigate, is how the same group of people form differently depending on the amenities that are close by, depending on what you can do, activities, how easy it is to get to people. Because that's holding that social network as constant and showing that geography really varies the social network. And then our current work is on new modeling approaches. So a little bit in terms of the nitty gritty of diffusion, power, et cetera, that I didn't show too much today, but I'm happy to talk about in the future. So thank you so much. I really appreciate it. And I'm happy to take some questions.
Fantastic. Thank you so much, Clio. If you want to stop sharing your screen, then maybe we can see all three faces. I'm sure that Levi and I have questions. But I see that we have one question already from Sandeep, who says, really cool visualizations and distance metrics. Thank you. Is the Mafia data openly available?
It is openly available. So the node link network and the families are openly available, and you can find that right on our Friendly Cities website. And I'll grab that and put it in the chat right now. And we want to thank Alex Singleton over the summer. I know that a lot of us contributed to his sharing of materials, and that's how we ended up putting it up here.
Excellent. Thank you so much. Mm-hmm. So to the audience members, if you've got questions or comments for Dr. Andris, go ahead and drop those into the Q&A. You should have the option to upvote. So if you see a question you really like, go ahead and give it the thumbs up. Karsten Kessler has a question also. Very nice work, Clio, he says. Have you looked into using more sophisticated network analysis tools from GIS and potential applications to social networks, something like location allocation?
Yeah, that's what we want to do next. Location allocation in terms of maybe putting amenities in the social network, putting amenities near the social network.
She might have frozen.
Yeah, it appears. Uh-oh.
We definitely have time for a few more questions.
Indeed. So
there we go. Well, we have another question, but I'm just waiting for Dr.
Yeah,
Andris.
we'll wait for confirmation.
Oh, my internet kicked out. I'm back.
You're back. You look like
I'm so sorry.
No.
I thought I had offended somebody, and I was like, oh, geez. I'm back. Yeah, Karsten here. Well, I get a do-over then. That's good. So we are using a couple of optimization type of methods, Karsten, but we haven't done location allocation yet. I'm not sure, we can't change the social network, but we can compare it to what something optimized would look like. And we did that with one thing called the flattening ratio, which took a network, our Mafia network and another network. And what it did was it said, hey, if we were being stingy about link length, like let's pretend link length was a fence and we wanted to use the least fences possible, could we still maintain that network degree distribution, et cetera? And if we optimize that and we're stingy, how much different would it look like than the real network? And that ratio ended up being, for our network, ended up being about 0.176 for our network. And for family ties, it was higher, so it was less efficient. And then for non-family ties, it was lower, so it was more efficient. So that's the answer.
Excellent.
Okay.
The next question is from Irma Hafiz, who asks, the questions keep moving on my screen. My question is related to data prep and cleaning. How hard is it to decode text, i.e. the Mafia data set, into actionable, readily used data?
We should work with a sociologist. They do it already for you. I'm just kidding. It is hard to do. So like that example, they had to take it from the actual paper in the library. But of course there are ways to scan digital documents in there, but it's pretty negligible, but it is very hard to just say, here's a relationship between two people, which is very complex and has a lot of information that we'll never even know about, and just say, okay, you're a line now, and we'll put a number on this line. So that's the hard part, is the simplification. The data prep is pretty easy.
Great. Karsten has a follow-up. He says, I was thinking of something like, where should I move if I want to get to know Big Frank?
That's a good point. You're right. So when we did, we don't want to impose too many normative values in this, but there is definitely some options to have to have you get to know your social network a little bit better and think about where you might want to go, where you might want to move to, etc. Students are using people use snap maps, which is like Snapchat, and seeing where all their friends are, for example. And they have been making decisions about like who to visit and that type of thing based on the locations of their friends. But that's a really good point. And I think that we could use more location allocation modeling with these networks. Yeah.
Great. Irma followed up with she's working on an Instagram activities from teen users, and it's a mess. That's a direct quote. Irma, if you wanted to drop that into the chat, then it might be easier for Dr. Andris to pick it up if she wanted to look at it later. And then Irma says, okay, now I have to search for a sociologist friend.
I'll take a look at that. Thanks. It sounds really interesting. Teenagers are really cool.
I think Neil Cunningham is about to ask a question as well. So we'll have additional ones, I guess. One thing I thought was really interesting before Neil gets the questions in was the sort of mismatch between the topological and the spatial in that last kind of analysis you showed. There's some really interesting substantive dimensions that you could explore with that, right? Like that there are areas where people reside, but they're not connected in those areas. And they're like, because our expectation would be that you're connected to the people that you're near to, right? But identifying those spots seems like it could be a really fruitful mode of analysis. So are you concerned about the statistics that they don't match? Or is it sort of that there's an opportunity there that there's this difference between our expectations about geography and connectedness?
Yeah, it's a good question. So I think you bring up a really good point that we should have some sort of underlying hypothesis about how many people would be connected, and then compare that baseline hypothesis to find out. Because as of right now, those scan statistics are completely descriptive. So they could benefit from some more, I don't even want to say like Bayesian type of knowledge, because that would get very deep into there. But given the expectation of how connected the degrees are in the entire network, and then sort of convolve that with some sort of distance decay, you could definitely do better there. I completely agree. It's been funny, it's cool that you mentioned the topological issues. Whenever we've seen the term spatial network scan statistics, spatial's network moving window, but it's always on the road network. And it's always saying we weren't able to find a cluster because, or we found a false cluster because in Euclidean space, the dots were close together, but it actually didn't work. So they did it on the road network. And that sounds really hard to do. And I'm really glad that other people did that. But when we do see those, when we do Google searches and search for that type of thing, we always see them on the roads. Mm-hmm. So this is sort of trying to capture non-planar connections. So the topology is different, you're right.
Yeah.
But I was interested, I think Levi's right that there are so many unexplored issues. And especially in the second example, what I thought was unexplored is maybe the temporal component, right? Because what you're kind of interested in is if you've got somebody who's really, really connected and really powerful, and propinquity matters, do people move in? I mean, do you aim for sort of geographical proximity in order to gain access to that person? And also sort of, especially when you're looking at the entire US, I was thinking, how many destination areas for Italian immigrants were there that are not part of this network, right? Are all of the cities kind of covered? And if you have some that aren't, and how does that work? Did people migrate to then basically expand territory? And that of course is happening for a time. So that's really interesting.
Yeah, what we do know is that New York was a big hub to bring people, and then they did move westward. One place that was really interesting was Miami. There wasn't a central family there, but there's a lot of Mafia members in Miami because everyone sent their representatives from their family down to Miami to take imports from Cuba, like rum and cigars and stuff like that, and also gambling. So that was one part of the country that had a ton of people, but it was like very free. But the other types of clusters in the country were very, they did unfold towards the west.
I was trying to see if I could pick out Las Vegas, but then you moved through the map kind of quickly. So I don't know.
Through the map kind of quickly.
No, but it's super interesting, right? To sort of think about how these cities, even though they're far apart, are really tied together by these different kinds of family networks. So yeah, Niall Cunningham has a couple of questions. The first is that your sample is self-selective. And so can these methodologies work as effectively with harder to reach populations? And then I'll go ahead and give you both parts. And then also, to what extent was the clustering of these millennials, so this is referring to the Big Brothers Big Sisters project, a random effect or a knowing/conscious drive to congregate on their part?
So the clustering effect of millennials is something that Rachel knows a lot more about than I do, where they tend to want to live and the types of being downtown, being in apartments, et cetera, like that. It's very tied to life course stage. So it's not a random effect at all. So congregating, I don't really know in terms of that, besides the normal demographic information that we have. But the conscious drive to be part of Big Brothers Big Sisters is the question I have, is that did they participate in that because a friend told them, oh, you should do this, you should do that. Whereas that type of information and influence didn't propagate in terms of the suburbs. Like, oh, I'm in this program, you should really do that. Or maybe the people in the suburbs are more in doing other types of volunteer work, like again, like Meals on Wheels or something where they need a car to do that, or something at a religious institution. So I know that doesn't answer your question completely, but it does talk a little bit more about that millennial pattern that we saw. And yes, the sample is very self-selective, absolutely. The methodologies that we used on the non-planar dyad network could definitely be used for other types of analyses where you do have dyads. One thing that we didn't go over was kind of the star and we see that a lot too, is that there's one ego, one person, and they have a star of connections, and then another ego and a star of connections. So that one, we have other methods that we can use for that one. And by harder to reach populations, maybe you mean, I know that what I mean in terms of harder to reach populations, maybe people who are struggling, or youth, or some type of population that may be less connected. But I'd be happy to expand on that too.
Yeah, I mean, you could imagine with, say, undocumented immigrants, for example, that you're really sort of curious what these chains are like, especially across space and across people. And that might be kind of tricky to get at. And it's actually a really nice example of where the qualitative aspect merges really nicely with this sort of, because you need boots on the ground, I suppose, to talk to people.
You do. And the epidemiology community has done a very good job of that with needle sharing networks, HIV networks, and that type of thing. And I think that they really, really lead the pack in terms of sensitivity and privacy and all that stuff.
Yeah, I had one more question, but I'm gonna leave it to the end because I can see that we still have one question from Mira Zhang, who says, thank you for the talk. What are your thoughts on how to study the effect of social networks on geography? You mentioned it in passing at the beginning, and I think it's super intriguing.
A good question. I think that it has to do with a lot of power dynamics and a lot of money too. I think that the social networks of who gets to build things and why are really important. And now that I'm in a planning department, I think about those things a whole lot too. I mentioned very briefly in passing, and I think Rachel just mentioned it too, like chain migration is a really interesting way to study how social networks impact geography in terms of like if you have ethnic enclaves or even the Mafia too, like people know each other and then they move different places. But the demand on the built environment for relationship entities, whether it is a cafe or whether it is an escape room, et cetera, especially now that people tend to be doing more activities than shopping, that is another way that relationships are changing the built environment. People want to do stuff with other people, and parks and movie theaters and stuff like that. They want to meet that demand too. It hasn't been as much movie theaters as restaurants, but it's a good question. It's a hard question.
Yeah. Well, we're almost out of time. And there's just one last comment, I think, unless I've missed anything. And if I have, my apologies, but from Abudu Asoman, who says, very insightful presentation, and that they hope you will make the code available. And so
absolutely. So we are working on that, our tutorial. And if anybody wants to do stuff in Python, I'm happy to collaborate.
That's great. This was fantastic. Thank you so much for doing this, Clio. I really enjoyed it, and I think our audience did also. This was a very nice set of questions, so thank you also to the audience for your participation. We're back the same time next week with Pedro Amaral on spatial regression in Python. But thank you so much. The recording will be available for today on YouTube some point in the near future, so if people missed it, if you want to go back and watch again, feel free. Yeah, but thank you very much, everyone, and have a nice rest of your day.